when I got kicked off, then when I restarted the session, I didn't hit record again. So we're going to miss something, but thank you, Kelly, for pointing that out. You guys are going to get a in between when I restarted my router, and now there's going to be a lag in the recording. So apologies for that. But I guess your victories in the Kahoot won't be recorded. So yeah, but anyway, yeah. So there's a lot of very interesting macroeconomics things happening, and it's a bit unfortunate because when I'm teaching like an undergraduate course, then you can really talk about this stuff a lot. There's a lot of like hand waving and I don't know, the debt levels are too high or whatever. But in this course, we're moving on past that sort of hand wavy, simple macro 101 or macro first class in macroeconomics models where you kind of just wave your hands and say output is equal to income, and when people have more income they spend more and stuff like that. That doesn't exactly make sense. So now we're going to be looking at more specific models where it more shows the way things can happen when people aren't just being fooled all the time. So to give you an example, how do you get the effect of a stimulus? How do you get a stimulus to have any effect at all? Well, you need to have prices be sticky, or you need to have information be hard to get. There has to be some sort of friction that's going to cause sort of firms or households to make decisions that they wouldn't have made if they could adjust their prices and things like that. So in a sense, the models are going to be a bit drier, unfortunately. But there is really a lot going on right now that's very closely related to macroeconomics. Also in Denmark, if you follow the news here, there's an economist at KU named Carl Johan, I believe, Damsgaard, I believe. He's the head of the Economic Council here in Denmark, and he's also been weighing in on when is it too much, when is it too little, how much should the government be spending now? So it's all been very interesting. But in any case, back to the somewhat drier economics models we're looking at here. So let me do this. I don't care about that little thing. Okay, so here is the solar growth model slides that I had on the recording that's on YouTube. Does anybody have any questions about any of these?
Yes, David, I had a question actually about you talked about growth rates in a video.
Okay.
And you did a mathematical derivation in which you also did something with integrals. And now that's been a long time ago for me.
Okay.
And I kind of wanted to have a further explanation of how you use it and why you use it. And yeah, I didn't really get that part.
Sure, no worries. So we get from, let's see here, it's this slide. Let me take a look here. Right, so this is almost like a definition. Okay. So we're going to define a growth rate. Oops, let's make that a little nicer looking. We're going to define a growth rate to be G if if the change in A over time, so remember this A dot T is equivalent to, I believe I have all this stuff on the video, but A dot T is equal to dA dt. So the change of A over time is G times the level of A. Okay, so this is just a definition of what we mean by a growth rate. So let's see here. So sometimes it's called exponential growth. And what I'm going to do here is derive this expression here at the bottom, which says that that if A is growing at rate G, then if we want to find the level of A at any time T, it's going to be our initial level of A times e to the power gt. So that's what we're trying to do here. Okay. So what I'm going to do first is I'm going to take the derivative of the log of AT. And I'm not telling you why I'm doing that. I'm just doing it. I'm taking the derivative of the log of AT. So I'm going to see the way this thing changes over time. Okay, and then using this sort of Leibniz notation, you can multiply and divide by dAT. Okay, so then we're going to get the derivative of the log of AT with respect to AT, with respect to its argument, and then also the derivative of AT with respect to time. Okay, well, we've defined AT here, or A dot T, as the derivative of A with respect to time. So I'm just going to replace that here. And then if you have the derivative of the log of X with respect to X, that's equal to 1 over X. That's just a log, that's an identity. It's one of those derivative rules. Okay, so you're going to end up with this expression. And then using this identity here, you can see that if we divide both sides by AT, A dot T divided by AT is equal to G. Okay, so I'm getting that here. So what have we learned? We've learned that the derivative of log A with respect to time is equal to G. Okay, so that's what we're driving on this line. The derivative of log AT with respect to time is equal to G. Okay, now comes the integral part. So let's take the integral of both sides. So the integral of the derivative of log AT with respect to T and the integral of G. Okay, so we're taking the integral on both sides. Well, the integral is also known as, I should say, the integral with respect to time. So the integral is also known as the antiderivative, right? So it's going to sort of undo this derivative. So in other words, I'll just say it here. The integral of d, let's say, x of t dt with respect to t is going to be equal to simply x of t plus a constant. Oh, is that right? Maybe I don't even need a constant there. Yeah, I don't even think I need a constant there. I should be careful. Technically what I'm doing here is I'm taking this derivative from 0 to some time t to be totally formal here. And that's why you would need a constant. Yeah, if I'm doing this, now I'm confusing myself. 0 to t, then I would just do this from 0 to t. No, that's wrong. Sorry. Okay, so it's here when it's the when I'm just taking the derivative without having, I forget what you call it. It's not a definite integral, it's an indefinite integral. That's when I need this constant, which is what I'm going to put here. Okay, so if I apply this thinking to this thing over here, then I'm going to get that the integral of d log at dt is just going to be log of at plus a constant. Okay, so it's got log of at here. Here, if I take the derivative, the integral of g with respect to t, so if I take the integral of a constant with respect to t, then that's going to equal t times the constant, and again, I believe plus c plus a constant. See, now I'm going to call it c prime. I feel a little bit not super confident in what I'm saying here, but I can double check later. Anyway, whatever. So anyway, what we get is log of at is equal to some constant. You see we have two constants here, so I'm just going to put a constant here. I'll call it c plus gt. Okay. And then when t is equal to 0, we're going to have log a of 0 is equal to, this is 0, is equal to C. Okay, so that's how I got this expression here. I can replace that C with log A of 0, our initial level of A. Okay. Right, so I've derived here that log A of 0 is equal to C. So now I'm going to replace log A of 0 here, and then you can see that this expression with that replacement is equal to this expression. Okay, and then the very last step is actually very straightforward. I'm just gonna take the exponential of both sides. So if I take the exponential of the log, the log goes away. And then over here, there's one extra step. So if I have the exponential of log A of 0 plus gt, that's the same as the exponential of log A of 0 times the exponential of gt, using a property of the exponential function. Okay, and then now you can see that the exp and the log are going to cancel. So I'm just going to get a0 and then times e to the power, the exponential of g of t, g times t. Okay, so I think that's exactly what I did on the video, only slightly more confusing when I did it in front of you guys without thinking about it carefully before I did it. Yeah, I think that when you do this indefinite integral, that's when you need the c here.
But that's more clear, David. That's I just needed some more intuition behind the integrals, and I think I got that now. So
okay, excellent, thank you. So yeah, I mean, the way you can see this is if you take the derivative of both sides, then you're going to see that this c is going to disappear, right? And then you're going to have the derivative of x of t with respect to t, and then here you're going to have the derivative of x of t with respect to t. So yeah, that's why you need it. And then here the same thing. If you take the derivative of both sides, you're going to get g. Okay, anything else? What else can I talk about from these slides? I think there's another derivation here. So like one thing that often students have a little bit of a question about is thinking about this little k of t, and then why is it that here with big K of t, I subtract off only depreciation, but when I have little k of t, then I'm going to have s of y of t minus the growth rate of A plus the growth rate of labor plus delta times little k of t. Like, why is it that this is here and only this is here? So I'm not sure if you caught it in my video. That's just a question that I think students often have, but there's a lot of intuition there. So little k is equal to, so I'll write that here. Little k is equal to big K divided by AL. So if you want the break-even level of little k, then you have to realize that these guys in the denominator are growing all the time. So you not only have to offset the depreciation in capital, you also have to offset the fact that these guys, the level of human capital is exogenously getting bigger over time. So that's why the break-even level involves not only depreciation, but also the growth rate of human capital. Everything clear on this slide about the growth rates?
Yes, I think I have one more question, David.
Go ahead.
You also have that you converge to a steady state of capital, or to the balanced growth path state.
Mm-hmm.
And you said that it happens when the capital is like farther away, it takes bigger steps. So how does that
Yes.
work?
Okay, so when the capital is farther away, it takes bigger steps. Okay, so by the way, thank you, Mariana. I see your question here. I'll go through that next. But if you take a look at the distance between these two lines, that's like the investment minus the break-even investment. So what you'll see is that when we get very close to the steady state, then the difference between the investment and the break-even investment is very small. So that means that the step size is going to be smaller, like the rate at which we're increasing. This is all continuous time. But over here, the rate we're increasing is the difference between these two lines. And over here, the rate we're increasing is the difference over here. So when we get closer to the steady state equilibrium, then we're going to be sort of, the level of little k is going to be growing slower than when we're farther away. So it's simply the difference between these two lines. You can make it formal, I believe. If you think about how this, where is it now? Do I have, yeah, I wrote it up here. So, you're asking a question about the size of this object here. Okay. So imagine we were to take the derivative with, so it would be the derivative of this thing with respect to t. Then, let's see here. Yeah, exactly. Then what you're going to see is, so this y of t is our little function that we had from before, which is concave, right? So the derivative of yt is, oh, I should be careful here. This is with respect to t. No, this would be the derivative of this object with respect to little k. Okay, so now that I've made everybody confused, let me actually say more formally. So you're asking about what's the rate of change of this. What is the rate of change as we get closer to the steady state? Let's think about the rate. Another way to say that is, what is the rate of change as the capital stock grows, at least in this direction? Okay. So how do we think about that? Let's take the derivative of this thing with respect to k. Okay, so we're going to take the derivative of k dot t with respect to k. Let me find some open space here. So let's take the derivative. It's going to be the total derivative, I guess, of k dot t with respect to k. So how does k dot t change as we increase the level of capital? Okay, so we're going to get s times the derivative of y. I'm going to drop the t with respect to little k, minus GA plus GN plus delta. Okay, and then here we're going to have the derivative of little k with respect to little k. So I don't think we need to write that again. Okay. Now this thing here, that's equal to what we've called f prime of little k minus GA plus GN plus delta. So what you can see here is that as we grow little k, this object is getting smaller. Okay. And as long as this is bigger than that, then the fact that this thing is getting smaller means that we're getting closer and closer to zero. Okay. Of course, once we pass the steady state, then this thing here is going to be smaller than that thing. And then that's going to mean that we're actually getting farther from zero once we pass the steady state. So let's actually just take a look at this. So I think if we were to write dk.t, dk, say dkt, got t in the numerator, I should probably put it in the denominator, dropped it everywhere else. Okay, and then let's let this be 0. So I think this is going to look something like that. Where this is the steady state level of, that's a star, steady state level of K. Does that make sense? Let's see. Yeah, this shouldn't actually be, I don't think this should be dk, right? This is just k dot of t, not dkt. Yeah. This is just a change in the capital. So I should get rid of that dk. Looks like this. This is just k dot t. My apologies. So yeah, so what this says is that when we're far away from the steady state, the change in k is going to be bigger. And when we're closer to the steady state, it's going to be smaller.
I think that's clear.
And then this is the slope. So this would be the slope then. Yeah.
Yeah, that makes it quite clear.
And it doesn't, no worries. This doesn't have to be, linear, of course, but it should be negative. The slope should be negative. Okay. So that's that. But anyway, yeah, that was like the probably more confusing, more formal version, but the less formal, but maybe less confusing way is just to look at this and notice that the difference between the investment and the break-even investment is like the amount of new capital you get. So when you're farther away, the step size is bigger. When you're closer, the step size is smaller. And then same on this direction, right? Now it's like investment, the shortfall in investment relative to the break-even level is bigger when I'm farther away from the steady state and then smaller when I'm closer. Okay. Now about golden rule. Again, you can sort of look at it formally, but let's look at it informally through the graph, which I think is maybe even more intuitive. So you can kind of, before we look at this savings line, let's just look at, don't look at this SHF of K. I just don't have another graph that doesn't have it on there. Let's only look at the production. Okay, and let's look at the break-even level of investment. Okay, so forget this savings times production line here. Okay, so if we think, what is our steady state consumption level, or in steady state? Recall that in steady state, we have this relationship. So I'll just write steady state. We have the relationship that savings is equal to break-even investment. Okay, so we have this relationship in steady state. So since this is our savings, this is our savings level at some steady state, depending on our investment level at some steady state, then it means that the amount that, suppose that our steady state were here, the amount that we're consuming is production minus our savings. Okay, so the amount that we'll consume is the difference between production and then the amount that we're saving. Okay, so, depending on the savings rate, you can see that I can kind of shift this line here, this SHF of K. Now look at that. I can shift this line up and down to sort of hit any steady state, any point on this break-even investment line. What's the savings rate that's going to maximize my consumption? It's going to be the one that maximizes the distance between production and savings in equilibrium. Okay. So what we want to do is we want to maximize the distance between these two lines. Okay. And then that level of savings, whatever that is, maybe it's, whatever level of savings is going to give us this line, that's going to be like our golden rule level of savings. Okay. So, how do we find this, the level that's going to, the savings level that's going to maximize this distance? Well, you can kind of think about it this way. If we're down here in this part of the curve, you can see that the distance is not maximized, right? The distance is kind of small. And if we move a little bit to the right, what happens? Well, the steady state line goes up. The break-even investment curve goes up, but the production curve goes up even faster. Okay, so by moving a little bit to the right, we can actually increase the distance between these two lines. Okay, now let's consider the point like way over here. Now you can see that if we increase savings a little bit, this line is going to go up a little bit, or this line is going to go up, and then this line is going to go up only a tiny little bit. So we're actually decreasing the distance between these two lines if we go any farther to the right. Okay, so what we want to do is we want to keep increasing our capital until the point where the slope of the production line is equal to the slope of the break-even investment line. Why is that? Because to the right of that, we're decreasing the distance between the two lines. To the left of that, we're increasing the distance between the two lines. Okay, so that's going to be the point where we're going to maximize this distance, which is our steady state consumption level. Okay, so that's kind of the intuitive way to think about the golden rule level of savings. And here it is as a picture. So the idea is, you're going to try to find the point where the slope of those two lines is the same. Okay. I'm glad you think so. I always feel like when I'm trying to explain these things on the fly that I'm not being as clear as I could be. Yeah, I think there's maybe another thing to say about it. What else is there to say about steady state, about the golden rule level? Nope, can't remember what it was. I think there was one other point to make. So yeah, if the government could choose the savings rate of the household, this is the level that they would choose to maximize consumption. In steady state, I remember what the other thing I was going to say was. This is actually an instructive point. Okay, so suppose that, let me draw this in a new place. Let me find my, oh boy. I'm going to save that, so I don't want to do that. I'm just going to draw it here. All right, so let's suppose that we have an economy that looks like this. And suppose that the golden rule level of capital would be up here. Okay. So now the government is thinking, this is like our current level of savings. And the government is thinking, let's increase that, let's increase S. Okay, let's increase the level of savings. Why? Well, we have a good reason, because we want to increase it up to the point where our equilibrium is at the golden rule level of capital. Okay, that would be like the savings level that's going to give us the most consumption in steady state. Okay, but here's my question: what happens at this point? Okay, what happens? We're sitting at this equilibrium. Suddenly, the government increases the savings rate. What happens to consumption?
It drops.
It drops. Exactly, it drops. So what actually happens, if I were to draw sort of a picture of consumption over time, try to do that with a little bit better line. Okay, our consumption at steady state is kind of constant. this would be consumption per unit of human capital would be constant. So I'll call that little c. Our consumption is constant. And then the government then decides at some time, this is time, that they're going to increase the savings rate. Actually, our consumption is going to drop. It's going to kind of go like this. Let's see here. Let me do that again. It's going to go like this. And then it's going to plateau at some higher level of consumption. But notice that for quite a long time, we actually had lower consumption. So depending on our discount factor, of course, you can put a lot of things into utility, but depending on our preferences, this could actually be something that makes us worse off, even though consumption at the steady state is at a higher level. Okay, so that's an important point to make. By the way, I can see that I've lost now more than half of the people in the class. So I'm not sure if that's just the way it's going to be, but I guess it is what it is. Typically, I guess at some point, we don't have any, your exercises are due next week. So typically at some point I would want to switch from sort of just a general Q&A to going over a problem or two from the exercises. But obviously we don't have that today, so. So yeah, there's that, there's this about whether or not capital levels can explain why some countries are rich and some are poor, and the answer is they can't. And again, it's because of decreasing returns to scale. Eventually, you have to really massively change the amount of capital you have in order to get small differences in output, which is basically what's operating here, is that we have to have massive differences in capital levels in order to explain differences in output. Any other questions about anything? The solo model, other parts of the course? Okay, so then I guess maybe we just leave it here for the day. And what I owe you guys, I still have to re-record the Ramsey growth model, which I'll do over the next day or two. And then you have your problem set, which is due next week. So then next week when we meet, we can have the general Q&A, and then we'll also go over a problem or two from the problem set. Okay, so as always, write me an email, suggestions, anything. I will try to make the Kahoot questions a little longer so you have more time to think about them. But otherwise, yeah, thanks a lot, and I'll see you next time.
Thank you.